Hello everyone, welcome back to this channel. The topic that we'll be exploring today is an essential part in every computer system called databases. And it is only a chapter in your syllabus, but then when I was studying computer science in my degree, databases is a course. So before we dive deep into today's chapters, I would just like to ask you for a favor. And according to YouTube analytics, over 74% of you have not subscribed to my channel. So if you have found my videos useful and you are an A-level student, please consider subscribe to my channel. That's the only favor that I'll ask from you. Thank you so much. So now let's dive deep into what we're going to learn today. I'll start out with why a file-based approach is bad for a computer system, and then dive deeper into what a relational database is. We'll go through terminologies and build a database from scratch. So let's look into what are some of the limitations of a file-based approach. A file-based approach would look very similar to how we store data in Google Sheet or Microsoft Excel. It looks like that. And one of the limitation is that when we are using file-based approach, there's no validation to detect, for instance, in this case, duplicated products. Look, there are two product Bs here. And there is also no validation to detect invalid currency. In this case, it should be GBP, pound, but then the typo is not detected here. And then there's also no validation to detect missing data. So these are the issues that affect data integrity. And the lack of inbuilt control when data is entered will cause this issue. Besides, it will also cause data privacy issue. For example, in this database here, we are clearly storing customers' data, like house phone number. So in this case, anyone can view this data. There's no access control to it. So it causes problem to data privacy. And I think the biggest problem of using a file-based approach is data redundancy. It is defined as being the same data stored more than once. So in this case, I have three different tables, data, and their purchase history and product details. If we were to store all our data in this form, you would see that there are certain data that have been stored in more than one places. And this is problematic because the more unnecessary data we stored, the more space we need. And in computer science, space sometimes means money because you need to spend more to purchase a bigger hard disk or cloud storage, etc. So data redundancy is a problem in a file-based approach. So data inconsistency is another one. So in this example, I'm storing member data in two different places. But then inconsistency could happen, let's say, when the employee make a typo. So instead of James, which is my name, James here, and it could be spelled as Jam, Jame. So this causes data inconsistency. So meaning the same information is stored in multiple locations, and yet it's subsequently updated differently in those locations, resulting in conflicting or contradictory data. So when you read the data, it will be like, oh, which one is the correct one then? Data inconsistency. And some of the data dependency concerns, so in the past, programmers created programs and designated necessary data files, while each department had its own program accessing specific data files. To ensure program functionality, programmers need to understand how data was structured in this file. So let me explain. What this means is that as the programmer is coding a program using this data, they need to know the order which these attributes appear. So this makes the programmer's job very rigid and make the program very inflexible. So this is one thing that concerns a file-based approach when you have multiple data depending on each other in different tables. So here are some of the items here. Another way data dependency is problematic is that let's say you want to add a new field, e-wallet details, to be added into this table. So because similar data are stored in multiple tables, you will need to add this data into many different tables. So as a result, it makes things very repetitive. So imagine you have 100 tables. It will mean you have to add the e-wallet details to 100 different data sets. So that's some of the limitation of a file-based approach, which is why we are learning a relational database approach today. So I have a definition here. I will first read it out, but then it can be quite difficult for me to explain the benefits of a relational database in just one sentence. So I hope that you stay with me for like 5 to 10 minutes. I will go through the terminologies of relational database and how to create one. So in that way, you can see progressively what are the benefits of a relational database as compared to a file-based approach. So a relational database is a type of database that organizes data into tables, which can be linked or related based on common attributes, enabling efficient storage, retrieval, and management of structured data. So in this example, I'm creating two different data sets, one containing the data of students, the other containing the data about a course. So let's go through the example one by one. And some of the terminologies I want to go through. The first one, logical view, a virtual representation of data derived from one or more table using SQL queries, providing user or application with a simplified and customized perspective of the database content. So what it means is that a logical view is a part of the data we take out from the main data set for a user to view. It's not actually stored. So let me explain in the next slide. So for example, let's say I have a data set that has all the students, but I only want to see students who have achieved the grade A. So in this way, I can use a query, which I will go through it in the last part of the video, to get a logical view of the data. That means I only see students who got achieved a grade of A. So some of the other terminology include attributes, something we read from the definition. Attribute is like the data that we are collecting, like student ID, name, age, grade, course ID. So these are called attributes. And whereas view is another name for attribute as well. So record here stores a particular record for, in this example, a student, meaning one record will contain the student ID, name, age, grade, course ID, etc. Right? Another thing that is super useful in a relational database is the primary key. So look at this table here. Primary key has to be an attribute or field that is uniquely identifiable, meaning it cannot contain duplicated value. In this example, we cannot use name as the primary key because two persons could have the same name. Similarly goes to age, grade, and course ID. The only thing that is unique here is student ID. So this is why in our database here, student ID is the primary key. So another way we can represent this database is to write down the attributes and then underline the primary key. So the importance of it is so that it ensures data integrity by not allowing an attempt to insert a value for a primary key when the value already exists. So in this example here, it's very important for a university to not create the same student ID for two different students. And that would cause a lot of trouble if this happened. And by using a primary key, it enforces the rule that, hey, you cannot enter another student ID that is 1, 2, 3, 4, 5, 6, 7, 8. So it allows unique student ID to every single student. Another terms, candidate key and secondary key. So a candidate key is a unique identifier, like the primary key here. It doesn't have to be primary. Some of the field can also be a unique identifier. Whereas a secondary key is an alternate identifier that is not the primary key. So in this example here, I don't have a secondary key, but a good example could be their preference, their secret question, etc. So the fourth key that we learned is the foreign key. So in this example here, I'm showing you the visualization of the two tables, one for student, one for course. So you can see that for course ID here, an attribute in the student table is actually the primary key of another table. So this is essentially what we call a foreign key. It's a field that establishes a link between the two tables, in this case student and course, referencing the primary key of another table and enforcing referential integrity. So what is referential integrity? It means that when, let's say I want to add another row into the student ID, and I try to enroll this student in a course that doesn't exist. So for example, when I'm typing C2003, I accidentally make a typo to make it C2004, which is a course that's not available. But because course ID is a foreign key, the database can detect that, oh, you're entering an invalid data. C2004 is not one of the courses. So another way I want you to see how a relational database ensures data integrity by not allowing the user to enter a record that is not valid. So this is how a foreign key ensures referential integrity. Now, I'm going to show you how to design a database from scratch, and stay with me for 5 to 10 minutes again, and then you shall be able to see the benefits of a relational database. So the first step of designing a database is to conduct an entity relationship modeling. So it is a conceptual data modeling technique used to represent the relationship between various entities in a database system. So these are the enormous data that you are collecting. So this process will help you to organize this data into their respective tables. And the scenario that we will be doing here, let's say the football court agency needs a database to handle bookings for a football team. Each team has a number of players. Each booking is for a football field. Each booking might be for one or more team. So it might sound complicated. That's why I want to break it down. Choose the entities, the first step. What are the entities involved? First of all, is the football team, and followed by how many players they have, the football field, and booking. And we can connect these sentences together using some diagram and relationship. So the relationship is that a football team has players, booking is for a football field, and booking involve one or more team. So I'm gonna do a football. So this is how we can draw out the relationship. Football team has players, and booking related to football field and football team. So now, after we identify the relationship, we want to decide on the cardinalities. So cardinality refers to the numerical relationship between entities in a database. It means whether it is a one-to-one, one-to-many, many-to-one, or many-to-many relationship. So let me give you an example. A football team, we played the first statement. A football team, it can have more than one players. And when you draw out the entity relationship modeling, this is the symbol to signify it has more than one players. And the reverse relationship would be a player must belong to only one club. This line here, it signifies that players can only belong to one club. So with that, we have our basic diagram. The second thing that you need to take note of is whether it is compulsory to have one player or one football team, meaning the minimum requirement. So in this case here, it says that a football team must have more than one player. It cannot have just one player. So this is why I use a more symbol here in the secondary quote. And then a player here must also belong to one club. So I have put a 1 here. So let me show you another example in order to make it clear. Another example is booking with a football field. One booking is for one football field only. You cannot make 2 football fields booking. And one football field can be used for many different booking. Yet a football field might not have any booking yet. So in this example here, I'm going to do the first statement. One booking is for one football team. So one booking is only for one, cannot be more than one. That means that's the minimum. And the maximum is also 1. So I have 2 dash symbol here. And the reverse relationship, a football field can be used for many booking. So the maximum is that it have maximum many booking. And yet it could be empty, like no one had booked the court. So this is why instead of putting a 1, I put a 0 here. So hopefully these 2 examples show you how it works. I'm going to prepare the last example. A booking may involve many football team. A booking might involve many football team, but it has to be at least one team here. All right, so that's how I put it 1. And one football team might make many bookings, and at the same time, they could also be making no booking in that particular week. So I have 0 to many. So this is how we decide the cardinalities of the relationship. once we have settled all the individual diagram, we can just put them together. And here you go. We have our entity relationship modeling. And that is just the first step of creating a database. The second step is to create a logical entity relationship model, meaning I just add a logical in front of it. So if you want to implement the diagram you draw just now into a real database, you need to do this. So in this case, you have to write down what are the attributes that you want to put in, and you have to also make some refinement to it. So in this example, I have a one-to-many relationship. No refinement is needed. Same goes to one-to-one, meaning I just write down the ID, the attributes that I want, and that will be about it. And then this team ID is a foreign key to the football team table here. So another thing that requires refinement is the many-to-many relationship. Now we have a problem. See, both the football team and the booking tables, they have foreign key of each other. But then it causes a problem because one table needs to be created before the other. So if booking table is not created, you can't create a football team because you don't have the booking ID. But then if the football team is not created first, the booking doesn't have a team ID to refer to. So this is why it's hard to make the table first, which one to make it first. So this is the way we solve this problem, is to create what we call a link entity, another table just to store the foreign key for both tables that we want to connect to. So in this case, instead of storing the foreign key into each of the table, I create this football team and booking table respectively first, and then I create a link entity to store the foreign key that these two tables are referring to. So hopefully this is not so complicated. Now, let's try to do some real stuff. It's a real case life scenario, but at the same time, I'm also introducing the idea of normalization. So normalization in database design is a process of organizing and structuring data, which I will be doing in a while, to reduce redundancy and dependency, ensuring that data is stored efficiently without unnecessary duplication. So in order to show you how to do normalization, I prepared another example. Imagine that this is the form that the football field is distributing to all the teams when they want to make booking. And then these are the data that we are collecting: booking number, court venue, booking date, team name, number of players, local. And what are the teams that is involved in this booking, especially. So the question is, if you are the database designer, how would you design a database for this particular example here? Now, without normalization, let's say you're only using a Google Sheet to store your booking data. This is how data will look like. One booking, it occupies 3 different records here, and because there are 3 teams who is involved. In this case, we have a major problem, which is data redundancy. How is it redundant? Look, you're storing booking number, court branch address, blah, 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 all this data many, many times, even though they are the same thing. And this is a problem, and we want to solve it. And before we proceed to the normalization step, you need to understand what repeating group is. So a repeating group in the context of database design refers to a set of related data fields that can occur multiple times within a single record. So meaning these are the data that will repeat over and over again. So the reason why we want to understand repeating group is so that we can go through the first step of normalization called 1NF. The first step, you will need to split the data into 2 groups. One table containing the non-repeating group, which is from booking number all the way to booking date. And the other group will be the repeating group, which will put team names, number of player, local, and then add a foreign key related to booking number. So I'm just creating a visualization here. The correct way to write it is actually like that. So essentially, I'm splitting the repeating group and also the non-repeating group. Now, once you have gotten into 1NF, you can now proceed to 2NF. What we can do next is evaluate each non-key attribute, meaning non-primary key, and determine if it relies on both components of the compound key. Any attributes dependent solely on one of the elements in the compound key should be transferred to a separate table. So now I have a team booking table here, but then if you look at this table, you will see that some of the attributes are dependent on the primary key. For example, number of players and whether they are locals or not. It depends on the team, because that's why when you put team, you create another table called team, putting in the team name, number of players, local. You are essentially separating this table into two different tables, and then just refer to it using a foreign key. So now that's 2NF. So after 2NF, we should have 3 different tables already from the major one. I split it. The first step, separating the repeating group. The second tab, reducing the non-key attribute dependency. So the last step is to do 3NF. Identify if there's any non-key dependency, meaning attributes that are depending on each other, yet they are not primary key. So in this example here, branch address 1 and 2 is related to the court branch, and this is not a primary key. So I'm gonna take 1, 2, 3 attributes out of the table and make a new table, branch info. If there is a new table must be defined, which is what I have here. So after 3NF, these will be how I will be designing my database, meaning in the DBMS that we'll be talking about later, I'll be creating table booking, table team booking, table team, table branch info. So some benefits of normalization. You can see that if we were to store our data in this fashion, whenever a new booking is booked, I don't need to create replicated data. I just need to add one more field here. So normalization in database design enhances data integrity and reduces redundancy by organizing data efficiently. I don't have to store redundant data by categorizing my data into this way. All right. Now, let's look into the software that allows database designer to create a database, which is called Database Management System. It is a software application that facilitates the creation, organization, retrieval, and management of data in a structured and efficient manner. So I want to introduce the 3 levels of a DBMS: internal, conceptual, and external. So as for the internal level of a DBMS, it refers to the lowest level and deals with how data is physically stored, accessed, and processed at the storage level. How is it stored in your hard disk or SSD, etc. It includes details such as data storage structure, access path, and indexing. And it is usually handled by the DBMS. So this is sort of abstracted from the user. We don't really care about what is happening inside the hard disk. So the second level is called the conceptual level. It's also not used by the user, but then the database administrator. He is a person who oversees the design, implementation, and maintenance of a DBMS, ensuring data integrity, security, and optimal performance, which is basically he decides how the data will be organized into different databases. So you will likely be this person after your computer science degree. And it represents the community view of the data. It defines the logical structure, meaning how to categorize data, like what we are doing just now. Constraint, integrity rule, without specifying how the data is stored or accessed. So the third level, external level, is related to user. An example would be if you try to sort through a list of videos on YouTube, this is what they will be presenting to you. You don't have to know how to create a database. They do it for you. You are just accessing the data. So this is the highest level and represent how individual users perceive the data. It defines the way each user group sees the data relevant to their task, providing a customized view. So in the example just now, I want to only see students who achieve a grade of A. So in that case, this is what the user will tell the program. I only want to see a student who got an A. He doesn't have to care about how data is structured and called. This is external. And the importance of having this layer is so that the DBA that we talked about just now, they can limit the access to data to certain users. So in this case, It provides a control and restricted access to the underlying data, allowing them to grant specific permission to user or application based on their need without exposing the entire database. So think of all these three levels as abstraction. You don't need to know so much under the hood if you are not required to. And it also ensures another thing that file-based approach couldn't provide, which is data privacy, which is set by the DBA. So here are some of the facilities provided by a DBMS. It provides tools for developers to interact with and design application for the database. And it also provides a user interface for a user to interact with the database, allowing users to perform tasks such as data entry, retrieval. Regarding data retrieval, I will talk more about it in the last part of the chapter using SQL, and you will see how powerful it can be. And a query processor interprets and executes queries, which is something we'll do in a while, translating user requests into database option. And last but not least, it can also create a report. So some of the functions that will be used by a DBA, the second level, conceptual level, defining access right, meaning it gives rights to the user to control and grant permission. So it can assign permission to this group of user and the other group of user, and it ensures data privacy. So another thing is data dictionary. They utilize the data dictionary to maintain metadata, providing a centralized repository for information about the database structure, relationship, and constraint. Last but not least, backup, which is essentially backing up the data. So the last function that will be used by DBA, I created a visualization here because it's a bit hard to explain, which is to create an index for rapid data retrieval. So for example, if I want to find the data 54545, like the ID, without an index, I'm going to go through the first row, look at whether it's correct or not. If it doesn't match, I'll go to the next row, go to the next row again and again. So this process, as shown by this nail here, is inefficient because the table could grow in size, like 1 million rows. So we don't want to do that. So creating an index, what it means is that we are creating a data structure that contains a sorted list of key, meaning I sort this ID here, and then I create a pointer field that points respectively to this data. So by sorting this out and pointing it to the record, I can scan through the data a lot quicker because I know that they are sorted. Maybe I can start in the beginning of the list instead of going through one by one. So of course, for now, you can't really see the efficiency of it because you have not learned hash table and B-tree. So this is something we'll learn in chapter 23, and then we'll come back here and to show you how effective it can be when it comes to data retrieval. So now, the most exciting part, in my opinion, for this chapter, the SQL, which is a form of programming language you use to create a database. For now, we have learned the process of creating a database, and now you will learn the language to use it. So SQL is a language. It can be separated into data definition language and data manipulation language. So the example of a database that we will be creating in this video is a school database. So let's say we want to create a table. So this is when we use a data definition language. First of all, I'm going to create table. Create table is the syntax, the keyword. It defines the new database with specific column and data type. So I'm showing you an example of how to write that in SQL. You first write the create table keyword and what you want to name your table and close it with a parenthesis. So what's inside here is they are all the attributes that you want in your table. So in this case here, I define what attribute I want, and I also provide a data validation technique, as in limit, to which I can limit the amount of character to 50. And I also give each attribute a data type, and it also ensures data integrity, meaning people cannot enter any other thing than number in this case. Last but not least, our data table, which is to tell the DBMS which field I want it to be my primary key. So to visualize, this is what happened after you write the code. Student ID is the primary key with all the different attributes. So I have also created a table called course. which is the same thing, all the fields, and then I select the primary key. So another thing, remember, if I'm also creating a third table, enrollment ID. So this is the syntax of it. Besides, when it comes to altering table, instead of just deciding what the primary key is, you can also define which field is going to be the foreign key. So in this case here, student ID and course ID is the foreign key in this enrollment ID here, which is the primary key of both tables. So now we have declared the database, but you have not got data yet. So this is when data manipulation language comes in. So after I write down this syntax, insert into whatever table I am, write down the order which the field will appear in the table, and then followed by the keyword values, I can then put in all the data I want. And what happened is that these data will then be inserted into the table. So this is there are two methods. If you don't know the order of the table, you can write down something like that, parentheses followed by the field name. But if you know the order of the attributes, you can just insert data like that, which is a lot quicker. So this is the insert syntax. Again, I'm currently inserting my data into the course. What are the courses that are available? Now, once your table is populated with data, the user sometimes might want to retrieve this data based on specific criteria. So for example, this is my table, my student table, but what if the user only want to know what are some of the names? I only want the names. So this is when the select keyword comes in. You can write the select keyword followed by the fields that you want to select, the attributes that you want. In this case, I only want first name and last name. So first name, comma, last name. From is another keyword, whichever table that you want to take it from. And once you key in this SQL request, the logical view that the user will receive will be like that. Look, so this is another example of what a logical view is like. It's not the data that's stored, it's just a representation of the query that the user is making. So another example, if you want everything, the user want everything, instead of typing select course ID, select course name, instructor, credit, they can just put a star. Stars signifies that I want all the fields to be included. So this is what you will receive instead. Now, we'll learn more and more keywords in this example. Order by, sort the result set of query in ascending or descending order. So to do it in ascending order, let's say I want to select course ID and credit, and from courses order by credit, I will get, oh, there's a mistake here. I should be showing course name and instructor. But then you can see that the logical view that is provided, it has been sorted by credit. And if you want it to be sorted in descending order, you can just put another keyword, DESC, and this is what the user will see. Again, that should be in course name and instructor because I didn't select it. Now, data manipulation. So this is when another function of SQL comes in, the where keyword. It filters rows based on a specific condition. Now, imagine that this is my table, student table. I have 6 students, but I only want to see students who got a B in their grades. So this is when the keyword where comes in. Select star everything from student where the grade is equal to B. And once you key in the command and the DBS run it, this will be the only data that will be shown. So you can see that only students who got a B are shown to the user, where filter rows based on specified condition. So another keyword here, which is a very useful once again. Again, I have course ID, a lot of courses with their respective credit. So imagine the user want to sum up all the credits in the table. They can just use a sum keyword, a parenthesis, and put in the attribute name that you want to sum. And once the command is keyed in, you'll get result 10, which is the sum of 3 plus 4 plus 3, 10. Another function is the count function. Let's say you have a very big database, very big table, you want to count the number of records, you can just do select count. So meaning you are selecting all the fields from students. So the count keyword will give you how many numbers of records you have, which is 6. And average is the same. Instead of giving you the sum or the count, it just sum them all up and then give you the average. So if you add all the edges up, you will get 20.5, which is exactly what the AVG function average do. So the next command that I want to show you is the group by command. It's a little complicated, so I've prepared a visualization for you to see. For example, you have this table, and your scenario is that you want to count the number of students for each grade, meaning how many students got A, how many students got B and C, etc. So this is when you use a group by function. I can say, can you group this table based on grade? And what happened is that the DBMS will then group these records. This is just a visualization that I'm showing you based on their grades. So A student will be here, B student will be here, C student will be here. So what is, again, back to our scenario, I want to count how many students who got A, B, or C. So this is when I can use command like that. Select grade and then count everything from student and you group by grade. Meaning the DBMS will first group by data from this and then apply the count function to each subtable that have been created. So hopefully that's a way to help you understand group by. And then the table that will be explained is this. Count, they will see that A, grade got 2 person, B 2, C 2. So that's essentially what a group by function do. Right, so the last example that I want to show you, which is the most complicated. So I have now had the 3 tables here, student, course, enrollment. And enrollment will show what student enroll in which course. So the scenario here is that I want to get students and their enrolled course. Meaning I want to see, instead of showing just student ID, I want to show the name of them. So what you can do here, in this example, I'm using another command called inner join. Inner join, think about it, look at it. I'm selecting student dot first name. Look, this is how I access the attribute of this table. Students dot last name, course name, which is what I care about from student. And then our inner join enrollments on student ID dot student ID equal to enrollment dot student ID. So meaning I'm linking student ID here to this student ID field in enrollment table. So as you can see, not every student is in this enrollment table, only 1, 2, and 5. So once I do the inner join, 1 to 5, and I only connect, imagine I'm bringing these data and joining this table based on the student ID. And the result of it will be like that. So initially I only have student ID and course ID and enrollment ID. So once I join it, I'm putting the student data into the enrollment table. So now I can see which student is enrolled in which course and what's the course ID. So let's do one more round. Instead of seeing just the course ID, I want to see what course is John Doe enrolling in, what's the course name of it. So this is when I use another inner join. I'm joining courses here, course ID of the resulting table with the course ID in the course table. So once I inner join both of them, I want you to see how this data will be moved to the major table. And then you will see that, hey, now I have a full table of what the student is enrolling in. So now since I'm only selecting the first name, last name, and course name, this is when the final output of this entire statement here. So look, this is just one of the most difficult topic. If you still don't get it, you can watch it one more time. But then essentially, inner join allows you to join multiple tables based on the primary key. Remember, each table is related to each other by using the foreign key. So you can go through the step again, one by one, to see how I did this. So last but not least, I want to show you some of the easier command, which is update. So imagine you want to change students ID 1, meaning John Doe's grade from A to A star. You can just use the update command, set grade equal to A plus, where student ID equal to 1, and then its grade will have been set. All right, A star. And the last one is delete. You want to remove one or more record. Delete from courses where course ID is 103. You want to delete this course. And then after your command, this will be the resulting table. So that's pretty much it for databases. It's a long topic. And let me know in the comment section if you have any question. I'll be happy to answer it. With that, thank you so much for watching. Goodbye.